Okay, I'm recording now.
Okay, perfect.
All right, so what did we learn? So we talked to the media over QUIC guy. This was, what's his name? It's Kixelated?
Pixelated,
Yeah,
yes.
he started the IETF working group for media over QUIC, and then he left it because it just got a bit bogged down in like standards discussions, and he wanted to do something at like the library level, if was my understanding. Um, and also pursue like building it out as at the application level. So basically, what started all of this was as Malik told me that this guy told him that datagrams are bad and we should not use them. And at first, I was confused because I was like, okay, every single video game uses UDP datagrams. What are you talking about? And then
Mm-hmm.
it rapidly became clear that he wasn't talking about UDP datagrams in general. He was talking specifically about QUIC datagrams. But on top of it, also QUIC is better than UDP unless you do an extremely large amount of work and are very likely to get it wrong. Like you are not as skilled as
The quick developers.
the QUIC
So you should just use and basically anything that you're going to have to re-implement a lot of what Quick does, such as congestion control, on top of UDP if you're going to roll UDP, because you're not going to just blast packets out and not do anything. You're going to be doing congestion control. You're going to be doing retransmits for some stuff probably. There's a bunch of things you're going to be doing.
You're also going to be not necessarily using the most efficient like serialization formats. Like you are probably not everyone uses variants. Like some people don't even think to do that, right? So it's like stuff like that. So, but the biggest takeaway was congestion control, and this is where he was like, you should use QUIC rather than UDP. So basically, in raw UDP, there is no congestion control. You just spit it out onto the network, and like the network drops what it drops, right? And you actually there's no back pressure. There's no way for your application to produce less data when the network is getting saturated. So just the quality of the network as a whole just degrades. And that back pressure is really important to make sure that you are not sending more data than the pipe can allow. And just
Yeah.
UDP just doesn't give you that. You'd have to develop that on top of UDP at like the application level, right? The difference is QUIC for both reliable and unreliable data. It maintains congestion control on a particular QUIC connection, I believe. I don't think it's shared across connections, but it is on a single QUIC connection. There is congestion control. And what that does is it makes sure that like through the process of getting ACKs on actually both reliable and datagram packets in QUIC, these ACKs basically provide congestion control. And this is something that TCP already does out of the box. Like TCP, you get congestion control because you have back pressure because it's all reliable, right? So like you would use, so TCP is good because it has congestion control, UDP is bad because it doesn't. So then the question, and QUIC is good because it has congestion control. So the question then is like, okay, well, why not TCP? Like maybe all my game data should be going over TCP. And the answer to that is very obvious. Like you cannot cancel or deprioritize messages if you're doing TCP. TCP always has head of line blocking because it's only one connection. You could, in theory, have a pool of TCP connections and like multiplex data on top of that pool, and that's how HTTP1 works. It maintains like a pool of TCP connections. But that sucks, and it's like a lot of pain for the application developer, and it's
Yeah.
also not quite like robust enough. Like opening a TCP connection is slow and takes round trips and stuff, right? So if you want a dynamic pool where that pool can expand and shrink, like it doesn't work well, and it's also consuming more ports and all sorts of stuff that are practical problems, right?
Yeah. And another thing is that you cannot migrate connections.
Right.
For QUIC, you can migrate a connection. So if you're switching from mobile data to Wi-Fi, or you're switching Wi-Fi networks, the same connection can get migrated. All the data can keep working. Everything works smoothly.
Right.
Whereas TCP, you can't.
Right. With TCP, you would just like I guess slowly, maybe it's unclear. Like basically, eventually that connection would die, right? And then you'd at the application, like the application would have to like handle that and like reopen a connection to like the new person and like migrate all the state, which is a fucking massive pain in the ass for an application developer, right? Because most of the time people just maintain like a mapping of like, we have this connection and like here's the connection state, and so like that invariant is going to get violated now, and you'd have to like totally rework that. So anyway, so UDP versus TCP. TCP good because congestion control, bad because you cannot like prioritize or cancel different types of data. Once you put it in, it's in, and you can't get it, like you can't cancel it. What QUIC does is it does give you the ability to have both reliable and congestion control and cancel your messages. So with QUIC, basically what you're going to have is in your network, in the QUIC networking libraries in Rust, that's called Quinn, but you know, different languages have their own implementations. Like that thing has its own internal queue, and that queue has priority numbers. It's basically a queue of streams. And each stream is, you can think of each stream as a TCP stream, right? Except to open a TCP stream, it doesn't require a new port. It doesn't require new port forwarding. Like it is all
and
it
doesn't require a round trip.
It doesn't require a round trip, which is also hugely important.
Yeah. So each stream in QUIC each stream is just a number. It's just an ID that is constantly incrementing whenever you open a new stream. So each QUIC datagram basically contains this ID. When you open a new stream, you just increment the ID. There doesn't need to be an app for that or anything like that. When you send over your new stream with your data, the receiver just reads it immediately and just sees, oh, this is a different ID. This is a different stream. And just handles it. So there doesn't need to be any communication whenever you open a new stream. Streams are incredibly cheap. They just cost a few bytes.
Yeah, so it can be as little as 1 byte, I believe. And then because it's a variant, it can grow up to 4 bytes, I believe. And that's something that, again, like probably if you're doing this at the application level, you'd not even be using a variant because most people don't even think to do that. Yeah, and that's like embedded in the packet itself. And then the only real difference between QUIC datagrams and QUIC streams are that the packets for datagrams don't have a stream ID, whereas the packets for streams do have a stream ID.
And there's two differences. They don't have a stream ID, and they don't have a priority, which a priority is an entirely internal thing to whatever QUIC library you're using as the sender. It's not something exposed over the network.
Right. Priority doesn't get serialized into packets. It's purely at the library level.
Yes. And what the priority does is it's a starving priority. So because datagrams don't have priority, if you have any data that isn't datagrams, any streams, then the stream data will get sent first. And if there's too much stream data and not enough space for any datagrams, then no datagram data will get sent. And the datagrams can just get dropped instantly.
Yeah, and this appears to be like implementation specific, but this is like roughly what everyone does. They prioritize datagrams lower than streams. So partly because of that, datagrams are inferior to streams, right? And then the other reason why datagrams are inferior to streams is because not only are they just always prioritized lower, but you cannot prioritize datagrams with respect to each other, right? So, for example, if you wanted, do you want to explain this, Malik?
Yeah. Let me explain the whole concept of how you should send send position data where you want your position data to always be the latest.
And this is not
for
assuming
using
delta encoding. This is the not delta encoding approach, right? This is
not delta encoding approach. This is you just every tick, every 50 milliseconds or whatever it is, you take the current transform of your player and you send that across the network.
Yeah, and this is importantly this is the we only care about latest state type of thing, along with like let's just ignore jitter buffers for now, and let's say we only care about latest state, and therefore it's unreliable but ordered data.
Yeah. No. I think. Okay. Yeah. We don't care about jitter buffers. Yeah. So how this would work? The optimal implementation, from our understanding, is that you have a QUIC stream that you send the data. You open a QUIC stream.
Do we want to explain the naive implementation first?
The what implementation?
The naive implementation.
The what?
The naive implementation.
Naive? No, let's, okay, yeah. Why don't you explain the naive implementation, then I'll explain the...
So the naive implementation would be, first of all, maybe you just use UDP. You don't use QUIC at all, right? And if you're naive, you're probably not doing congestion control. So you're probably just sending UDP messages anytime your tick rate says send a UDP message. Maybe you have some estimation of like what that tick rate should be, but maybe not, right? And so it's like probably not dynamic to network conditions, or maybe you're just not doing congestion control at all, right? And that would be also, you can't like prioritize the position packets higher than like the VoIP packets or like stuff like that, right? Like if you have different like categories of data, if you're doing it on top of UDP, it's not super clear like how to prioritize that stuff. You're going to have to implement your own like datagram queue and then have your own application level priority system, and then also estimate like the network bandwidth based on like an acknowledgement system, and then based on the the number of packets like getting dropped because you're checking for those acknowledgements, you say, oh shit, okay, the pipe capacity is like less, so send less data, and now use the like application defined priorities to like choose which data we send in what order. And like that's literally what QUIC does, right? If you're not doing any of that, then you're just not being as smart as QUIC. And if you are doing that, then good for you, I guess. But like that's a lot of work, and again,
you're unlikely to get it right, is what what Quixel said. You've seen a lot of implementations that have attempted to get it right that didn't quite get it right.
Yeah.
So it's better to use QUIC.
So
the non-naive...
Wait, so that's the most naive solution, which is when you just use UDP, but then it turns out that the naive UDP solution is like actually really complicated to do it correctly, right? So then let's talk about the naive solution with QUIC. So the naive solution with QUIC would be use QUIC datagrams, and then you get the free congestion control and whatever. But now you don't have a way to like prioritize certain types of data higher than other types of data, because all datagrams are equal and they're all lower than streams usually, right? So that also kind of sucks. And let's say, and internally, because of the congestion control, because you are doing congestion control, there is an internal queue of both datagrams and streams trying to be sent. And so you, depending on how your library implements that, there might be like one datagram that is queued, or there might be like a whole line of datagrams that are queued. Probably it's just like first in first. Like it's probably just like one is my assumption, but I don't know for sure. Regardless, the point is that like you can't actually prioritize that information, although you are benefiting from congestion control, right? So
and also another part that makes this naive implementation bad is at the application level, you still need to do some sort of acknowledgement of something, because if you don't, for example, if you're trying to sync transforms of a player, you only sync it when the player moves. You don't want to sync it every time, right? especially if it's a lot of data. Like if you're doing VR and it's hands and head and hips and feet IK, you only want to send that when it's changing. If somebody has put their headset down, then you don't want to be sending that data, or there's a million reasons why. With the naive QUIC datagram solution, when the datagram gets dropped, it's dropped. It's over. So you're not guaranteed for the last bit of data that's the last bit of important data to actually end up making it over.
Right. So, and when I was doing like the the web transport networking library that I had been working on like more than a year ago, I had like a distinction of like, this is the reliable, like you want to like, I'm not going to change data for a little bit, so like make sure that this thing reaches its destination. And like that's like an additional like API complexity that is like just weird. Like and sometimes you don't even know. Like sometimes you don't know that this is the last piece of data you're likely to send, right?
Yeah.
So there's not like really a good solution. The good solution would be send all data as reliable, but like basically cancel it once you realize that there's like newer data available.
Yeah. And this is what the optimal QUIC solution does. So the optimal QUIC solution here is, because these stream IDs are so cheap, because it's so cheap to open a stream, you open a new stream, aka you increment an ID, every time you have a new position packet to send. Then what you do is, whenever you open a new stream, you take the old stream and you close it. And you reset it specifically.
Yeah.
So there's two API calls that you can use to finish streaming. There's one which is finish, and what that does is it will keep retransmitting until it's fully done, and then it'll stop. And it'll also tell the other end, the receiver, hey, I'm done. That was all the data. The stream is closed.
So it's kind of like flushing. It's kind of like flushing all the data, essentially.
Yeah, it's like flushing all the data. What reset does is it sends an error code, basically, and you can specify the error code. Like it can just be like close, and it stops sending data. It stops retransmitting. So if it didn't send all the data, or if it didn't send any of the data, it'll just say, hey, I didn't manage to send.
And just to mention it,
and just for and what's important here too is that how QUIC works is that it'll like compact the data that it sends over in a single UDP packet. So basically, for what Quixel said is those 8 bytes, which are the size of this stream is closed and this is the error code, are basically free, because you have it fits within. It's just added to whatever data is being put into the UDP packet that gets sent over.
Well, also the error code is also a variant, I believe.
Yeah. I think he said that.
Well, I'm saying that. Like I've seen that in the Quinn stuff.
Okay. So what you do is the optimal solution here is you open up a new stream every time you have a new latest piece of data, and then you call close on the old stream, and you drop it and you get rid of it, and you don't worry about it.
You call reset.
And what this does is, if the stream had already managed to send, it's fine. If the stream hadn't managed to send, then it doesn't send at all, and it sends a new piece of data, which is exactly what you want. If you don't have new pieces of data, then it makes sure that latest bit of data does get across. It'll try to retransmit it until it makes it across. And importantly,
well, it doesn't. Quick correction. Like, it's not that it's retransmitting it until it gets. Well, actually, yeah. I guess it does. You're right. My bad. Yeah, you're right.
Yeah. So what you get out of this is you get all these properties that you want, and you get all these properties that you want without having to worry about specifying it at an application level, and it's already done basically optimally. In theory, you could make a more optimal solution. You could implement a better version of this over UDP for whatever your specific application is. But it's very, very hard to get right. So it makes a lot of sense to just use QUIC streams for it.
Yeah. I mean, not to mention, on top of this, like, you're getting the benefit of, like, TLS. You're getting, like, a lot of other things that, like, in my opinion, are actually important and probably are just going to be written off as, like, oh, we don't need that. But, like, in reality, you actually kind of should care about that stuff.
I forgot another thing, which is that normally so in this case, what we're dealing with here, what you want for these position data packets is you want a sequenced unreliable packet, right? You want it to be sequenced. You want to be able to say, hey, drop the latest data on the receiver side.
Oh, yeah. So, this is an optimization. I would frame this as an optimization, basically, what you're about.
Yeah, so this is an optimization. So you could include a sequence number within the stream that says this is the sequence, and it's just, it's a U64.
Like whatever that would be at the application level. Like most of the time, the application developer would say, "Oh, like in my game's packet format, I have like a sequence number, and that's how like the receiving end is going to order them." Right.
But and this doesn't work on web transport. This doesn't work with the web API because it's not exposed. But it is exposed in the QUIC library. They expose the stream IDs. So you're able to just automatically, with the sequence and a reliable thing, you're able to use the stream ID as the sequence number and just make sure you ignore because routing, when packets go through routers, packets can arrive out of order of when they were sent. So you might get the data of your position like 3 frames ago after you got the position like 1 frame ago. And so now if you just accept those in that order, people will jitter and they'll rubber band and they'll do weird things. But you can just say, I only want to take the latest sequence, and then that won't happen.
Yeah. And what's important to point out, in case it wasn't already clear, is that a QUIC stream is reliable within the stream. So like I can open a stream and then you can treat it kind of like a TCP stream where everything inside of that is reliable. But streams are not, they don't block each other. Like there's no head of line blocking. They're all multiplexed on the same QUIC connection. So streams get multiplexed on the connection, and they're not necessarily like you can cancel a stream before the stream even gets sent. So like the life cycle of a stream is like not guaranteed to be.
Yeah. And if you have a higher priority stream that's sending a ton of data, lower priority streams might never end up sending any data.
Which is a good thing, right? Because what that means is that like your network is not big enough for like all of the data. So you only want to send the highest priority stuff.
And so let me give the example with the iframes and the delta frames of the video. So
wait, are you sure we should launch into that, or do you think we should hash this out a bit more? Like I feel like I just want to clarify.
Okay, I thought we were done. Continue.
So again to restate it, like basically when you're doing like position data where like you only care about the latest thing, instead of doing a UDP datagram because you're gonna have to implement congestion control and a bunch of other complicated stuff that you might not get right, you don't use UDP datagrams. You don't use QUIC datagrams because, like we said, there is no way to kind of like say, look, actually, why don't we use UDP QUIC datagrams? Because
we don't use QUIC datagrams because you can't cancel them. So if a QUIC datagram, well, 2 reasons. First, you can't cancel them.
You don't need to cancel a QUIC datagram because everything that the application is putting through is going to be newer. So like it's implicitly canceled by virtue of I'm giving you the newer data, and maybe your queue size is only 1. Although I guess if you don't know what the queue size is,
it's definitely no. It's not guaranteed that if you put a new datagram in the QUIC in the buffer that the old datagram will get dropped. Maybe the old datagram will get sent instead of the new one. I don't think there's any reliability guarantee.
That's true. It is probably implementation defined, right? But I mean, so it might be implementation defined. It might be that there's like 1 or 2. Datagrams. And then
there's the second, and so there's 3 reasons. That's the first reason. The second reason is if your latency is if your tick rate is 50 milliseconds and your latency is 20 milliseconds to a player, if that packet gets dropped, it can return. You can notice that it's dropped because other packets that make it will have a different stream ID, and QUIC will notice that there was a missing stream ID, right? Like it'll see that, there's some data from stream 1. There's some data from stream 2. There's some data from stream 1. There's some data from stream 3. there's no stream 2, I should send back a packet that says I didn't receive stream 2's data. And what happens when this happens is, what can happen, and the benefit is that it'll come back, it'll send that ACK that says I didn't receive stream 2's. Stream 2's will be resent before the 50 milliseconds are up, so it won't have new fresh data to send. It's still going to send that old data, but it'll send it in time so that way you'll still receive that position update, and then what is it, 10 milliseconds afterwards you'll receive another position packet.
I don't think this is quite accurate. I don't think it's that you observe holes in stream IDs. I think it's more that you observe holes in, like, it can't be that, right? Like,
no, he said it was that's what QUIC said, that it would notice the hole in the stream ID.
It's not that the receiving end notices the hole, it's that the receiving end acts anything that it receives, right? So the sender can detect the hole because it didn't get an ACK for it. And then what the sender does is it retransmits, because it said, oh, they didn't get it, retransmit. So basically,
we should ask again, because this was not what I thought he'd said. But I don't know who's wrong. Obviously,
I'm 99% sure that it works this way, because think about it. Like, the point of what you're saying is not which side observes the hole. It is that, like, the sender knows to retransmit.
Yeah,
right?
Yeah. At the end of the day, the point is what you get is, if your round trip, if your one half of round trip time, if your latency to whoever you're sending data to is smaller than the tick rate of your network updates, you can end up actually getting a smoother network than if you're doing it over quick datagrams.
Right. So let's restate this, because I think it was a confusing explanation. Let's say that your game sends data at 20 times a second, like it's IK data. You send it 20 times a second. So the period of time between each IK update at your application level is 50 milliseconds. Let's take two scenarios. One scenario is where someone is really far away. They're across the ocean. So, like, the round trip time between, like, their computer sending the IK data and, like, the server receiving it is, like, far longer than the frame time. Right? So in that case, like, they're going to send IK data, and if they cared about acknowledgements, right, then they would have to, like, let's say this was TCP, right? They send the IK data, and then they're ready to send more IK data before they ever receive acknowledgements that IK data was received. Right? Like, it might take, let's say, like 200 let's say they got really bad ping, like 200 milliseconds or 100 milliseconds round trip for them to receive that acknowledgement, but they're ready to produce data every 50 milliseconds. So what you actually want to do is you want all the data that's outgoing. If your, like, round trip time is longer than your frame time, you don't want to care about acknowledgements. You basically shouldn't be retransmitting that data if it wasn't received, because you already have new data to send. And that's, like, the inherent benefit of something like UDP. It's like, you don't care about retransmitting when you already have new data, right? But there's another scenario which is different, which is when the network round trip time is actually quicker than your frame time. So you might produce IK data every 50 milliseconds, but maybe it only takes 10 milliseconds to round trip between you and the server. So in that scenario, packets still may get dropped just, due to network congestion. And so you want to retransmit your IK data, because, like, you try to send it, and then you don't get the acknowledgement, so you're like, oh shit, I need to send it again, right? And you can do all of that within, like, before you're even ready for your next IK update, potentially.
Yeah.
Right? It just depends on the network conditions of the remote party. So what's interesting about, well, first of all, the problem with datagrams is you know, datagrams never get, well, it's not a problem with datagrams. Datagrams never get ACT, so none of this is an issue with datagrams, but we've already explained the other issues with datagrams.
Yeah.
But
Yeah.
but the naive stream implementation would be you open a new stream for every message, you send that stream, and then now because streams are reliable, the streams are going to continually like retransmit until the entire stream has gone through, right? So in the case where you've got a faster a lower latency round trip time, that's good because it means that more of your data is getting through successfully, right? You have more reliability. But in the case where the round trip time is longer than your frame time, it's bad because instead of retransmitting old data, you should just be transmitting new data. Right? So the solution to this is that QUIC streams, like we said earlier, QUIC streams have this like reset function. And what reset does is it basically tells the internal queue of your QUIC networking library to just delete that entry from the queue. So it stops trying to retransmit it, which means in the case where it's a really long round trip time, you don't waste network bandwidth retransmitting things that are already stale, right?
Yeah.
So it gives you like the nice properties of UDP while also giving you the ability to like have different things of different priorities while also having this like nice optimization with the stream IDs to encode that as like your sequence number, and also gives you the ability to have TLS and everything multiplexed, and also gives you the ability to cancel stuff and avoid retransmission because oftentimes you don't need that. But then in the cases where you do need that, it just does it for you, right?
Automatically, yes. And also importantly, unlike with UDP, you have to implement your own packet splitting, but across UDP datagrams.
Oh, true. Right.
But with the stream, if your size is bigger than the datagram's size, it'll just automatically split that up into multiple datagrams, which is a thing TCP also does for you, but all those problems with TCP.
Right. And the other thing as well, I think he said that it also batches datagrams together.
Yes. So for when it's a bunch of small data, and then also when it's a bunch of data that isn't the size of the datagram, because datagrams is pretty big. It'll put it all together in one. It'll do a bunch of size optimizations to stuff the data in there, and it'll also include congestion control and control flow packet in that datagram.
Yeah, and
so
that's not
it's able to do that.
As far as I can tell, it's not like, because I was like, oh, doesn't that like increase the amount of latency if you try to like batch packets together? But but batching is necessary on the sending end. Like some form of queue is necessary on the sending end because like you're using congestion control, and if you're not using congestion control, you're fucking up, right? So like assuming that you're using congestion control, that implies that like you can't always immediately send a packet. You need to queue packets because your congestion controller might not be letting you send yet because there's not enough network throughput. Not enough, your pipe isn't big enough to like push all the data you want through, so it has to provide back pressure in the first place, and it does that through the use of like a queue, right? So by having that queue associated with the congestion control, it can also use that queue to batch packets together into one larger packet, which is like more optimal for the network than like many UDP packets, right?
Yes.
Because you're saving on like the header of the UDP packet.
Yeah, and yeah, yep. Okay, so we did that bit. Should we talk about the
video
conceptual video one? Okay.
Yeah,
so
this part will be less relevant to Dooley, but I think this is more for our records now.
Yeah, this is for our records, and also Nick wants to listen to this, and Nick's going to listen to this.
Okay, who's Nick?
Because the creator of Stereo Kit.
Oh, okay, yeah.
So, and JC might also want to listen to this because JC had networking problems in the past and might be interested in this approach. So, for video frames, how video frames work in this theoretical concept is you have iframes and you have delta frames. And delta frames are based on the iframe.
No, they're not though, right? Like delta frames.
I know they aren't, but he said they were for purposes of the explanation. I think, right?
No. This was a big misunderstanding. Like, so the iframe is purely to allow people to join the video stream who weren't there from the start, right? It's like this holds all the information of a frame. The delta frame
it's like a PNG
is not
frame.
a delta on top of the iframe. It's a delta. It's a chain of deltas that all start from the iframe. But deltas are still dependent on the previous delta. Right? And that was the misunderstanding that I had. I thought all deltas were diffed on top of the iframe, but they're actually, it's not. It's a linear chain starting from the iframe.
Okay. So you have this iframe delta frame setup. So the iframe is basically PNG. Delta frames are diffed on top of each other, and they represent the changes every 2 seconds. You have a new iframe because you just want to make sure like everything's good. Apparently, some platforms will have a new iframe every minute. Like they'll really stretch it out unless something goes wrong.
Yeah, the main benefit there is like error correction combined with like someone new to the stream can join the stream, right?
Yeah. So in this video, you have a jitter buffer. You have a window of a couple of however many milliseconds where you try to smooth out the network latency because, or not the latency, the change in latency, the jitter. Because you'll receive some packets fast and some packets slow just because of how routers and networking works. It's not consistent. It's not a consistent speed. So what you can do, a really, really good or a possible good implementation with QUIC is you have your iframe, which is the very important frame that you need to send. Somebody who joins, you have this iframe, you set that at the maximum priority. What this means is it will starve everything else if needed. So if you can only fit iframe data or you can't fit all the iframe data, then it will just send the iframe data. Then what you do is for all of the you have these other streams that were sending delta frames. So somebody has joined, a new iframe decides to get sent out. What you do is for all of the delta frames that are too far out of the jitter buffer, you just close them. For all of the delta frames that are within the jitter buffer of the client receive unit, the jitter buffer plus the network latency, you deprioritize them. So, and then for the new iframe, you set it at the highest priority. And the reason you do this is so you make sure that the person gets the new iframe as soon as possible. But if there's any extra space anywhere in the datagram, in one of the datagrams that sends over, maybe because there might be multiple datagrams, it won't all fit in one datagram. In one of the last datagrams, there's some extra data that can fit some delta frames.
Yeah, I think
it'll send
not
those,
so much space,
and then you'll have a smoother video experience.
It's not so much space in the datagrams; it's more just network bandwidth in general. I think
it's both, right?
Yeah, it's both.
Because it will pack if there is extra space in the datagram. Because assumedly in this iframe, it's a pretty big image with a decent resolution, so it's not all going to fit in a single datagram. So there's going to be multiple, and there's going to be some space at the end. You can fit a couple of delta frames in the end, maybe. I don't know how big delta frames are. So it'll do that. And then also, if it just manages to send the iframe, then it'll send all the delta frames that it can too, except for all the ones it doesn't care about and it's closed. And this is an incredibly simple implementation that uses QUIC streams and all the features in it.
Is there more? I thought there was more explanation. Sorry.
I don't think so. Is there? Do you remember anything else?
I think it's important to talk about the alternative, right? The alternative would have been like you take your delta frames and you have a datagram per delta frame, or you pack them or whatever. But like basically, then you have to deal with like retransmission because as we said before, the delta frames are not just on top of the iframe. You actually need all the delta frames. So, but you only need the delta frames since the last iframe.
Yeah, so you order the delta frames you're sending over, their priorities aren't all the same either. So the iframe is the highest priority, then the delta frame right after the last iframe has the highest priority under the iframe. then the second delta frame has the next highest priority, and the third delta frame, et cetera, because they need to come in an order, in that order. So you prioritize them in that order, then they can be sent over in that order. You'll get some video data from the delta frames. All of them probably won't make it across, but maybe a couple of them will. You need to make sure that it's the ones that directly apply to the iframe that come across.
So the what I wanted to say was basically when he was explaining this, he was talking about like the jitter buffer, right? And he said essentially you still want, because you have that jitter buffer, you don't only care about deltas since latest iframe, you also care potentially about at least some of the deltas before the latest iframe.
Yes.
Right? So like the most naive situation without a jitter buffer would basically be all these things are sent like reliably. This is the most naive. Everything is sent reliably, right? Nothing gets dropped. That's bad because once something is older than your jitter buffer window, you don't need it anymore. So why are you like retransmitting and doing all that stuff, right? So those clearly should be canceled. So you shouldn't like you should use like either datagrams or streams with resets, right? Now the question is, why do we not use datagrams? Well, because as we said before, first of all this information actually does need to be reliable, at least since the last iframe. So like using datagrams would mean you'd have to like rebuild that reliability on top. Why would you do that? Just use a string, right? That's why we don't use datagrams. We don't just use streams and not reset them because we don't care about data that is older than our jitter buffer, right? We do want to cancel data and stop retransmitting it when it's too old, right? So that's why we reset streams. And then the question is just, how do you decide like when to reset a stream? And you basically reset it, you kill it, you cancel the stream when it is like out of your jitter buffer window, and you just deprioritize it the older it is in that window. So the priority allows you to still have like fresher data, and you're still sending as much of that stuff as you can within the network capacity, of course, right? But you still get to like intelligently like prioritize and like and kill old data and continue to retransmit the data that should be retransmitted, and you still get to have like your own custom reliability guarantees based on like your application's needs, which clearly are very custom because like you have iframes and delta frames, and none of that is encoded at the network protocol. That's like your protocol, right?
Yeah.
Can we talk real quick about the idea for the delta compression for IK?
I don't really remember how that works, so why don't you talk about it, and really I'll chime in if I remember anything.
We didn't really talk about it in the thing, but we briefly touched on it, and it mostly stems from ideas I had in the past that I complicated, right? So the basic idea would be like when you're talking about IK, it's like most of the time, like if you need enough, need enough like precision, especially in terms of like rotations and position. Well, really, and it doesn't matter. Rotations and positions, like you need enough precision to where like slight movements don't appear like jumpy, right? Like, so you need enough bits of precision in positions that are near each other and rotations that are near each other. I'm just going to say positions, but like when I say position, I might mean translational position or rotational position, right?
Transform.
Yeah, transforms that are near each other. So like, clearly, but transforms that are far from each other don't necessarily need as much precision, because the assumption implicitly is that people can't teleport. So they're not like if they are jumping from like a close position to a really far position, that means that they're moving really fast. And so it might just be like less noticeable to someone to like notice the lack of precision there, right?
Yeah.
So if you think about like how your bits are, like if you take like a floating point number line and then you mark on that number line like the positions of each number representable in like a discrete integer. By default, you have like a fixed distance between each of those positions, and I'm suggesting instead of having a fixed distance between each of the discrete positions on that number line, you have like a logarithmic distance where there's more precision more bits of entropy are allocated towards the quote unquote center point of that number line. And that center point is kind of like your iframe. It is like, this is the current like state associated with this connection between the two things. This is like where your precision center is located, right? And that precision center, like every update on top of that is going to be relative to that precision center, but not relative to each other. So unlike the video situation where you have an iframe and then coming out from the iframe is a chain of deltas, instead you have an iframe and then every delta is on top of the iframe. They're not on top of each other. Okay?
Okay,
and
So it's almost like the IEEE 754 floating point standard, but your center...
Yeah,
your mantissa literally just IEEE 754?
It's very similar. Like same idea, right? Your center is the mantissa, or sorry, which one's the mantissa is the floating point part, right? Like your center is the exponent, and the other thing is the mantissa. But the thing is, like, you don't actually it's slightly different, but it's the same idea, right?
Okay.
I think it's better to just say this is your precision center, and that's like a state associated with the connection, and then everything is like relative to that, right?
Yeah. So you're just sending across floats that represent the delta.
Well,
you are just sending across like floating point 8 numbers that represent the delta.
Call them floats because they are represented as like quantized, like they're like they are discrete integers, right? Like your precision center might be a float, but everything relative to that is going to be an integer.
Oh, I see. Because you don't need a mantissa because it's just a raw integer that then you map with a logarithm.
The analogy to mantissa and stuff is going to confuse more than it's worth. Like, just think of it as like we have a float, which is the center point, and then we have integers, which represent numbers relative to that with like a logarithmic range
mapping function.
Yeah, exactly. So the idea is, okay, well, that's great and all, but like, first of all, how do you make sure that like clearly your center point has to be reliable, right? So immediately, if you're just using UDP, like you'd have to build reliability on top of it, which sucks. So you could do it with like both a TCP stream and a UDP stream, but now we're getting a little complicated, right? But regardless, clearly your precision center needs to be reliable, and then all the deltas are all the relative values are unreliable but sequenced, right? And so what you would do basically is similar to the video case. You have a very high priority stream for your precision center, and that's guaranteed to be reliable, and also by virtue of being high priority, it's like the most up to date. And then you also have the delta values are in streams done after that point, so their stream ID is greater than the precision center stream ID, and because they come later, you know that they are relative to you know that they're relative to that stream ID, although that's not guaranteed on the receiving side. So let me hand wave over that, as that's just an optimization. Okay, so let's just say that every delta at the application level encodes the sequence number of the reliable center. Okay. So we're not using stream IDs. We're just doing it at the application level. Now what you do is every time you want to send an update, you're creating that pool of streams. You're sending these at a lower priority than the precision center updates.
Not a pool of streams. You're not doing a pool of streams. Right, you're just creating new streams.
Not a pool. You're right.
That was an important point too. And I just want to digress for a bit. An important point is because streams are so cheap, there's basically never a case where you want to create a pool of strings and reuse them like you would with TCP.
Why. That's not actually why. Like, it would be better to have a pool of streams if you could, because then you stop incrementing your number, which means that you have slightly more efficient packets, because that's a variant, and you're using, like, by keeping it as a smaller stream ID number, you're only using 1 byte instead of, like, 2 or 3 or 4, right? The reason why you can't use a pool is because if you're using a pool, you're not resetting your streams. And if you're not resetting your streams, then you're not able to cancel retransmission, which then defeats the whole point.
Yeah, and then you got head of line blocking.
Right. So,
yeah.
Okay, so resuming now what I was saying. So your center, your precision center, high priority stream, and it's reliable because it's a stream, and you never cancel it, basically. Mm-hmm. Your relative numbers, your relative transforms, are also streams. They're not datagrams, but they are essentially relative to that thing, and they encode the sequence number in them so you know which one they're relative to. And what that means is that, just like in the video thing, you want to retransmit this information because you want to take advantage of, like, congestion control, and, like, just because you can't transmit something this second, like, doesn't mean that you can't transmit it, like, before your next, like, position tick, right? So you still want to, like, do your best to transmit that data, and that's why, like, it being a stream instead of a datagram is, like, useful, right? But once you're ready to move to a new, like, center point, because these things are all streams, you can just reset any streams that haven't finished, that are older than your new, like, iframe, essentially your new center point.
Yeah.
So it's like
just
almost
iterate through a back of all the streams that you had and just reset them all and then start sending again. You don't even need to check their IDs because you just know.
Right. And so it's basically the same idea as the video thing, except instead of there being a chain of deltas, it's like deltas that are not stacked on top of each other, right? Mm-hmm. You only care about the latest delta. So, like, if you haven't yet sent that delta, you just reset a stream and create a new stream for the new delta, right?
Yeah.
But this means that, like, this is not actually that complicated. Like, as an application developer, that would not be that complicated. If you tried to do it with, like, TCP and UDP, you would need, so the center points would be sent over TCP, and that's fine. But you wouldn't be able to cancel old center points, first of all, right? And my assumption is that we're sending center points, like, pretty fast. Like, we're sending them, like, maybe every...
Well, I don't think if you did this, you would implement it with TCP and UDP. You'd probably just implement reliable data over UDP. Because then, like, that's what most game developers end up doing, right? Is they have reliability over UDP.
Okay.
For the data that they need to have reliability.
If you did it over TCP, I'm just saying, like, I'm just bringing this up as one approach, right? If you did the center points over TCP, you still have the head of line blocking problem where older center points are still getting retransmitted when they don't need to be, right? So you don't want to use TCP. You want to use something reliable over UDP. So let's say that you did that. Let's say that you did all that stuff and your library gives you, like, a reliable but sequenced, unreliable but sequenced UDP, like, quote unquote channel, right? So you would send those sequence numbers over that, and then how do you map your delta? Like, how do you get it so that your deltas refer to those sequences, right? You're going to need to enclose that information in your stuff, and you're also going to need to, like... Okay, the recording has resumed. So, where was I? Basically, yeah, so if you were doing it over, like, your own custom, like, unreliable but ordered UDP thing, you need, like, one channel, and it has to be its own channel, right? For just the center points, and then you would need a separate channel for every single, or maybe it doesn't have to be a separate channel for every single one, but you need a separate channel, at least one additional channel for the relative data, and then the relative data has to reference the other one using, like, the sequence number of the center point stuff. And
you have to re-implement all this stuff, basically.
Yeah, it'd be complicated, right? And I think that's why, like, when I brought it up, it was like viewed as like this is like very difficult, right?
Yeah.
And maybe I'm not being I don't know if I'm representing what the other party said accurately or not. I mean, it was a long time ago, and I don't know how well I explained it at the time. So, but I think that like this exact same approach, like a very similar approach to the like stuff that Kixelated was explaining with iframes and delta frames and stuff and video. I think we can use that exact same series of optimizations that he outlined for IK delta encoding, right?
Mm-hmm.
And just
Yeah.
the difference is that instead of iframes happening every like 2 seconds, that's not fast enough for what we're talking about. Iframes have to happen like very fast. Like they have to be happening like maybe 4 times a second or something, right? Or 5 times.
Whatever it is, we can figure it out. I mean, I don't know, honestly. Like, we might be good enough to do it every 5 seconds. I don't know. You'd have to just look at it and see. I don't think this is something we can theory craft from.
It might even be entirely dynamic in the application. Like, it might be the case that, like, when you move far enough from your center point, like, maybe the center point resets constantly every second, but, like, if you move really far really fast, then your center point is going to reset like even before then, right?
Mm-hmm.
And by having this system, I actually think that it like is flexible enough and easy enough to use to where like doing that type of thing isn't like crazy difficult. And in fact, like if you actually look at like what's happening under the hood of the network protocol, like on the transport layer, all of these things are the same, right?
Mm-hmm.
So both of them are just like sequenced but unreliable data.
Yeah.
It's just two separate
It's
channels.
just, but you have the ability to cancel it. So the thing that makes QUIC so incredible is it implements all these features for you, and you have the easy ability, which I haven't seen in other game networking libraries, and maybe I just haven't looked hard enough, but it implements all this for you very well, and it has the ability to cancel streams, to close streams when you've decided that, oh, actually I don't care about this data making it anymore.
With UDP, it's intrinsically going to be canceled, right? I think a better way to say it would be that QUIC.
Yeah, a library on top of UDP would have to have that and all these features.
Yeah, QUIC is giving you reliability, but without the downsides. That's a better way to describe it, right?
Yeah.
Yeah, and prioritization and stuff. Like it's all that niceness. I mean, you want like to retransmit because you want to saturate like the bandwidth available to you based on the congestion control. You just need an intelligent algorithm to be telling you what that optimal bandwidth is, and that's what your congestion controller is. So like you or your network library need to implement that. QUIC already implements it.
Yeah. And according to QUIC, it's very difficult to get right. That was like an incredibly important point that he made several times. It's like it's very, very difficult to implement congestion control, control flow, and all of these and the size optimizations and all that stuff. It's difficult to implement that well over UDP. That is a difficult problem to solve yourself as an application developer or as yeah.
Yeah. Cool. Well, we just talked for an hour. Is there anything else you want to say before we're done with the recording?
I think that was it. I don't know.
Isn't that wild that our summary of what we talked about is an hour?
Yeah. Yeah. I mean, I feel like 20 minutes of that was the IK was the new idea, but like, yeah, so 40 minutes of talking to the summary of what we talked about. Yeah, that's crazy.
I think the first 30 minutes and the first 20 minutes and the last 20 minutes are most applicable.
Recording yet?
I will now. Thanks. Bye.
Okay.